네. 네, 뭐 시간 됐으니까 바로 시작하겠습니다. 예, 뭐 다들 점심들 잘 드셨나요? 참 오프라인에서 편하게 물어볼 질문도 이거 물어보는 게 되게 애매한 질문이네. Okay, so to start with, I have two announcements. So let me share my desktop. Okay, so this is not it. It's in ETL. Okay, so as you can see, let me minimize this and then let me show you. Okay, it's working. Okay, so first of all, okay, sad news. I'm not sure it's sad or not, but this is sad for me. I prefer offline lecture, but we have the announcement this morning actually from school, and then there's a extension of this online classes lectures until 2 weeks more, so until the 12th April. So hopefully that's the end of it. But well, I'm not sure. So, but anyway, so for now, and we're gonna just continue on this online lecture. And sorry for that. And then again, and I mean, just if you have any kind of concern or issue with this online lecture or anything, just let me know, and I see if we can just resolve some issues together. But anyway, this is what's happening. So please understand. Okay, and then the second announcement was made and then 21st, and then that was about the homework one. And then again, you can just kind of go to the kind of main board in ETL, and then you can find out the homework one, and there are 9 problems you need to solve from the kind of chapter 1 and 2 out of the reference book. And then because that book is out of production, I just uploaded that kind of scanned copy of that kind of exercise or problem set parts, so you can just look at that kind of PDF file and then find out the problem numbers, and you can solve it. And then I just give you the kind of due until quite a long time, so you have times left, and then hopefully until then we can finish up the chapter 2 so that you can solve your homework. And then for the submission, you're gonna scan your paperwork, and then you're not gonna come to the office. You just scan your paperwork and then upload directly onto the ETL, so you don't need to come to school just to submit the homework. Anyway, so that's what's gonna happen. And then there's a kind of late penalty, so try to be in time. And then yeah, that's all of the homework one. Okay, so any questions regarding the announcements or any concern or anything? 혹시 질문이나 혹은 뭐 얘기하고 싶으신 거나 뭐 그런 거 있으신가요? 오늘도 채팅들 많이 해 주시면 될 것 같아요. 어차피 말들을 잘 못하시니까. Okay, so then alright then. So let's review the previous lecture quickly, and then we're gonna just finish up the lecture 1, and then we're gonna move on to the lecture 2 today. And then I'm just showing you this slide again because it has lots of important concept and information in it. So, please just bear with me, even if I'm just repeating this again. But this is actually the essential of what you're learning now. So again, we talked about the thermodynamic system last time, and then thermodynamic system is the things or substance, devices, or combination of devices you're interested in your thermodynamic analysis. So that thermodynamic system could be a very arbitrary one, that's your choice. And then again, could include a substance or device or any other things. And then, to begin with, what you need to do, you need to define the thermodynamic state and of your thermodynamic system. So again, the state is like your kind of dot. So it's just kind of given at a point. It doesn't have any history before. It doesn't have any history afterwards. It just exists at that point. So state is given, and then that's given. That's it. You don't need to worry about any other thing. It's just kind of given at the point. It's like the point. And then the state is, typically given by or determined by, and then, maybe today or probably next lecture we're going to talk about how many properties you're going to need. But anyway, thermodynamic properties are needed to determine the thermodynamic state. So if you want to say this coffee is a certain thermodynamic state, you need to give me a certain number of thermodynamic properties. Okay, let's just say that's two independent thermodynamic properties, like the temperature and pressure you give me, and then I know what that coffee is. That's thermodynamic state is set, is determined. So if I just have that thermodynamic, the 100 degrees Celsius 1 atm coffee, and then my friend has 100 degrees Celsius and 1 atm coffee, and we pretty much basically know we have this exactly same coffee, and then we are doing the same experiment. Okay, so that's the property. And 잠시만요. 질문 있었네요. 미안해요. 중간고사요. Okay, so the midterm exam, actually that's what I'm keep constantly talking with my TAs, TA for this lecture, and then how we're gonna do it if we need to do that online. And then, yeah, I mean, just if that's happening, I think there's no other way. We need to do it online, but we need to find a way and then make it like exam, not just homework. So I'm thinking about it. So again, there's a kind of possibility. And so I cannot say that's not going to happen. I would say it can happen. So I mean, for now, there's a possibility, but how we're going to do it, but I currently I don't consider any just homework or project. Instead, I still want to do the midterm exam itself. So, but how to do it online, and then that's kind of tricky one we're gonna figure out. 예, 뭐 중요한 부분이니까 한국말로 다시 말씀드리면은 일단 예, 이게 뭐 지금 사태가 이게 좀 길어지면은 뭐 시험도 좀 애매해지는데요. 예, 그렇다고 해서 지금 그걸 갖다가 프로젝트나 숙제로 대체하는 것도 조금 특히나 이 과목이 특성상 조금 애매함이 있어서 아직까지는 그렇게는 고려를 안 하고 있습니다. 그러니까 뭐 학교에서 무슨 약간 좀 지침이 내려오거나 좀 어쨌든 어떻게 생각해도 애매함이 있으면은 뭐 어쩔 수 없이 그렇게 될 수도 있겠지만 일단 허플리 그전에 오프라인으로 뭔가 그냥 좀 조심스럽게라도 이루어지기를 바라는 거고, 만약에 그 중간고사 기간까지 그런 게 안 풀어지면은 온라인으로 시험을 볼 수 있는 방법은 어쨌든 좀 예, 뭐 계속 그냥 TA하고 좀 고민하고 있거든요. 예, 그러니까 뭐 그 부분은 일단 그렇게 생각해 주시면은 좋을 것 같아요. 일단 시험은 중간고사는 일단은 본다라고 생각을 해 주시면은 좋겠고요. 예, 뭐 진행하면서 또 그 말씀드리도록 하겠습니다. 그 정도면 괜찮죠? 예, 감사합니다. Okay, so and then okay, so I just mentioned the states and then how the states are determined, and then it should be given by properties. You need to give me the thermodynamic properties to define the thermodynamic state. And then the process, again, is what's connecting these states. So process, you need to very much differentiate and from the states. Again, there are states, and the states are connected by process. And then during the process, there are only 3 transfers in thermodynamics as mentioned. So work, heat, or matter transfers. And then these are the 3 transfers occurring during the process. Again, these are not occurring at the state. State is like just certain point. There's nothing happening. It's just there. And then the process is kind of moving along. So you're moving across. And then that, transfers happening in the process, not at the state. So state, again, is a given point. So that's the important thing you need to, differentiate. Okay, so any questions about this? 혹시 뭐 이거 리뷰하는데 혹시 궁금한 거 있어요? 예, 감사합니다. 예, 넘어갈게요, 그러면. Okay, so this is too simple. So thermodynamic system and the categories you can just take a look at. I'm gonna just moving along. And then some example, just please take a look at it, and then you know all about that. And then thermodynamic properties, there are 2 main categories. First one is the extensive property, and then these are the properties which is proportional to mass. And then the other property is the intensive property, which is independent of mass. And then so you remember the mass, volume, energy, because if you have the 100 joule of energy in 1 kilogram of mass, if you increase the mass by twice, if you have 2 kilogram mass, your energy will be 200 joules. So energy is definitely extensive, like volume. And then, but the pressure and temperature, they are not changing across the, increase of the mass. It's just independent of mass. So these are the intensive property. And then there is a other kind, which is called specific property. And a specific property, again, is not intrinsic one. It's just a derived one. 유도된 거죠. It's derived one, and from the extensive property divided by mass. So it's from the extensive property, but because you divide by mass, and then that now becomes independent of mass because you normalize by mass, and then it has a characteristics of intensive property. So it's not really intensive property itself, but it has a characteristic of intensive property which is independent of mass. That's a specific property. And then the one good example was specific volume. And then in symbol we use the small v for the specific volume, and then we use the big V for the extensive volume divided by mass. So that was the specific volume, and then it is independent of mass, and then it has a characteristic of intensive property, but it's specific property. And then we just last time considered that classical thermal is continuum theory, so we don't care about the microscopic behavior or molecules and vacancies around it. So I just repeated already twice or more, so I'm gonna just skip it for now. So any questions up to this point? 없는 것 같지요? 예. Okay, 예, 감사합니다. 예. Okay, so then move on. And then thermodynamic state, again, state is like a point, and then the thermodynamic system is uniquely specified. Again, and this is important point, is uniquely specified. So meaning if I have certain thermodynamic state of certain substance, and then if your friend has certain thermodynamic state of a certain substance, basically, we are talking about the same thing. That's very important thing to start with when you just do the experiments, because you need to believe others, they're doing the same stuff, and then that start with the same thermodynamic state. So state is that important. And then there's a equilibrium state, and then the thermodynamic state is kind of the arbitrary one. It doesn't need to be equilibrium, but if we say equilibrium state, and then that means the property of the system, like the temperature, pressure, specific volume or concentration, and then those are all the uniform throughout the control volume. So meaning pressure being uniform, temperature being uniform, chemical potential or concentration being uniform throughout the CV, your control volume, and then don't change with time. It just kind of remains there, and even after a long time. So meaning it achieved equilibrium state. It's at equilibrium, and then that's kind of the a maximum entropy point, and that's what you're going to talk about later on. But for now, equilibrium state is uniform and then don't change over time. That's an important thing. And then state variables is kind of variables or thermodynamic properties. Those variables are thermodynamic properties which describe the equilibrium state. That's called state variables. And then whenever we say, this is the topic today, actually, and in the next lecture note, is the equation of state is the functional relationship. So this should be the functional relation. So it's mathematical form. It's functional relationship among the state variables. So these state variables, and then for a equilibrium system. Okay, so there might be, just if you're smart enough, you may just come up with certain equation of state for the non-equilibrium state. But anyway, this in the case is very obvious, ambiguous how to define the properties and things. So again, the equation of state, historically, it's about the equilibrium state. Just please kind of bear that in mind. So, and that's the equation of state, and typically given in PVT because these are easily measurable. So if you think of it, why not? I'm having the equation of state with the energy or entropy or specific heat, and then those are not easy to be measured. It just go through certain other processes. But pressure, volume, temperature, they are easily measured by just mankind device. So typically the equation of state is given in PVT. So that's kind of historic equation of state we can find out. And then one good example is the ideal gas equation of state. 이상기차 당만식 다 아시는 거죠. PBNRT. And then the van der Waals equation of state, which is we're going to talk about today much, actually. And so it's in a form of PVT relationship. And then again, if you're given two other properties, and then your thermodynamic state is given, again, we're going to come back to that point later on. But for now, if you know two thermodynamic properties, your thermodynamic state is given, meaning if you know V and T, your pressure is known. So as you can see, it's PVT becomes 0. So that function gives the equation of state. Or if you know P and T, your volume is known, or P and V, and your temperature is known, so forth and so forth. So this is how you write it, or you can just write it in this explicit form for the pressure. So pressure is a function of V and T. Okay, so you can just do the similar thing for the V is a function of T and P. Doesn't matter. Okay, so this is the equation of state. Okay, just stop me if you have any question. I'm going to just keep moving on. And then I think this was the last point we were discussing last time. So the process, again, the process, was happening between, so if you have these two states, and then process is what's happening in between. And then the process is a path of state change. So you're doing state change from state 1 to state 2. And then this is what's happening. That's called process. And then states during a process, and then depending on your experiment, measurement, and then, just pretty much based on your situation of your thermodynamic experiment. And then you may know at any instant of that process, you may know your system's thermodynamic state, or your system remains very close to an equilibrium state. You may say that as quasi-equilibrium process. Again, I'm emphasizing again, there's no such thing like the equilibrium process because nothing happening in an equilibrium way. There's always some driving force and then moving along. So meaning there's always some non-equilibrium amount. But, if it's negligible, and then whenever you just measure something, you can find out the uniform state at that, process, during that process, you may say that as a quasi-equilibrium process, meaning in this plot on the right bottom PV diagram, so you start at here and then end up being there. But, what you do is you basically measure by this frequency, and then at every of this measurement, your thermodynamic state, and then that's very close to equilibrium state. And then you may have that as a just single solid line, and then you can just assume that as a quasi-equilibrium process. But if your measurement is precise enough, or your non-equilibrium status is too long enough, you can observe in your experiment, then you don't know what happens in between. You cannot specify the thermodynamic state of your substance or thermodynamic system during the process. In that case, again, in this kind of PV diagram on the right bottom, and then you just have just dotted line. What you only know is the initial and the final state, and then you don't know what happens in between. So you just, you're just gonna make it straight and then dot it, and then that means you don't know anything in between. You just know the initial state, the dot and dot. I don't know what happens between. So that's called non-equilibrium process. Again, there's no just clean cut between the quasi-equilibrium and non-equilibrium process. That's totally of your judgment, and then that also depends on your experiments and then your analysis. So if the non-equilibriumness is important for your analysis, you better have the discretion on that non-equilibriumness. So meaning, yes, I have the non-equilibrium here. But if that's too much kind of small and too much negligible, or for example, entropy generation sense, if the entropy generation is small enough, and you may just assume that that's clean and then quasi or close to the equilibrium process, and you just assume it in that way, do your analysis, and then you will have the errors, but small in engineering sense. So again, that's your discretion. Okay, so that's the quasi equilibrium and non-equilibrium. And then the last point I made was the reversible versus irreversible. And then again, actually you made all good points last time when I asked the question. And then reversible, irreversible means this is about the process. So this is the right question. Is this the reversible process? Is that the irreversible process? So it's about the process. It's not about the state. So you're asking certain process being reversible or certain process being irreversible. So that's the right question. So what that is so you just meaning that you're moving certain state to the other state because you're talking about the process. So you've done that process. So moving from one state to second state. And then I'm asking you, is that reversible process or irreversible process? That's the question. And then what you need to do is, just one good way is actually you can evaluate the entropy generation. So we're going to come back to the second law later on, but you already know the second law. If you can evaluate that entropy generation during that process, and then you may say whether that's reversible or irreversible, that's okay. But more, intuitive sense, actually, that's what I kind of how I described it last time. So what you need to do, okay, so you've done that process. So I wonder that's reversible or irreversible. Then what you need to do is you need to make it back to the original state. So your thermodynamic state, you move it back to the original state, but reversible way. And then you come back to the original state in a reversible way. Because your system coming back to the original state, your system didn't change at all. But now what you need to look at the universe, whether there is any change or not. If there was any change, and then your initial that process was irreversible. But if you could come back to the original state without changing the surroundings in the whole universe, and then your initial process was reversible. Okay, this will be more clearer when we deal with the second law discussion. And then, but for now, I think this is it. So before I move on, any questions regarding any of these topics? 이해가시나요? 질문 있으세요, 혹시? 네, 감사합니다. Okay, so then the last one down here is the ISO certain property process. That's all you know. This is the process where you have certain fixed property, so being the constant property. So meaning if you have the isothermal process, your temperature of thermodynamic system remains constant during the process again, and the isobaric and the pressure being constant during the process, isochoric and the volume being constant during your process. So I think I can just do some quick example for this last one. So constant volume thing. So what you can do is you can just put the gas inside a fixed size of the box, and then let's do the process. The process here, I'm gonna just do the heating of it. Okay, so even if you do the heating, and it may create certain temperature distribution, certain pressure distribution, but we know that the volume of the gas will not change because it's inside a fixed box, and then that's isochoric process. So again, so this iso some property process doesn't matter what other properties, how they are changing or non-uniform anything, it doesn't matter. I mean, if that property being a constant, and then we can still call that isothermal. It doesn't matter, it's reversible, irreversible, quasi-equilibrium, non-equilibrium, if you know something. I mean, just in this specific case I just drew, this is totally non-equilibrium process if it's fast enough of heating. But anyway, so I mean, if you can fix either of these, and then you still can call iso some property processes. Okay, so let's move on to the next. So this is the last topic of the chapter of the lecture note 1, which is about the temperature. Again, one time I mentioned that the thermodynamic is unique in that it deals with temperature. So meaning if you can just, just remember when you learn the Newton's physics law, or, quantum physics law, and then you never talk about the temperature there. I mean, just, okay, so quantum's law, I mean, in the energy wise, you have a temperature there, but so for the Newton's physics, so it's F equal ma, and then action and reaction, and then those. It doesn't have any temperature. So the temperature is, I mean, if you also remember the solid mechanics and then other things, and then they're not talking about the temperatures. So temperature is very unique in a properties that within the thermodynamics. That's why there is the zeroth law of thermodynamics, which is about temperature. Okay, so again, in temperature, I mean, if I ask you, what is temperature? That could be the very kind of a vague question. I mean, it's not vague question itself, but the answer will be vague. I mean, you just say, well, is that degree Celsius, or is that hot and cold? But they are not all about it. I mean, just temperature, you may feel that is very, comfortable with that and with the concept, with the notion, but how to define it, how to understand it, that was actually a big issue in the beginning of this history of thermodynamics. There was kind of big discussion going on. So anyway, so temperature, this is what you know out of the just kind of common sense. But as I mentioned, is very hard to be rigorously defined. And then one way of defining it, it's not really definition, but one way of talking about it. And then this is it, the zeroth law of thermodynamics. Okay, so to talk about the zeroth law of thermodynamics, we need to understand the thermal equilibrium first. So, and then as written down in the second point, if two objects in thermal contact for a long time, so meaning you have some object A, some object B, and then you just make them thermal contact. Thermal contact doesn't need to be really the contact. If this is a radiative heat transfer, you can just make it like that, like the sun just give us the radiative energy, the heat transfer to the earth. But anyway, so you just make them in any sense do the thermal contact, just allow the heat transfer for a long time. So, in the meantime, you may see something just heat is not really be seen, but you're kind of seeing pressure is changing along during this process, or I mean, just because we're not knowing temperature yet, so other measurable properties, they're changing along. And then after a long time, after this thermal contact, now it just kind of stop, and then there's no more state change, and then we don't see any more change. And then people just say that as thermal equilibrium. Okay. So meaning they only allow the heat transfer. They don't allow the pressure imbalance and then moving piston around. It isn't allowed. It's just only about the thermal contact and then doing the heat exchange. But we're not talking about the temperature yet. So, but people say, okay, thermal contact, and then make something flows, and then after a long time, it doesn't change anything. It doesn't do anything anymore. And then, okay, so because we allow the thermal contact, and then we call those two objects are in thermal equilibrium. Okay, so that's how they just define the thermal equilibrium. And then what the George law of thermodynamics is this. So if two systems are separately in thermal equilibrium with a third system, these two systems are in thermal equilibrium with each other. That's the direct law of thermodynamics. Again, this is based on experiments. This is based on observation. This is just what people observed, what just mentioned. So you need to believe it to start to talk about the thermodynamics, because this is a direct law, and then this is all basis for the temperature measurement. Anyway, so this is how you write it in some symbols. So you have the object A, and then you have the object B. Again, we're not talking about the temperature yet, but anyway, so let's use the temperature here. We're going to just come back to that. So, and then this A, object A, is in thermal equilibrium with certain other object C, thermometer, let's say that's C. And then this object B, separate object B, is thermal equilibrium with the thermometer, or C. And then what the George law of thermodynamics tells you is TA will be the same with TB. Does this law make sense to you? 이거 영법칙 이해 가세요? 무슨 얘기하는지 아시겠죠? 이해 안 가시네? 이해 가시는 거죠? 어떻게 보면 그냥 상당히 트리비얼해 보이죠? That's sounds trivial, but you need to believe it if you want to use the thermometer to measure something. Because you never say, so this is your coffee, and then that's your friend's coffee, and then I use the thermometer here, and I measure the 100 degrees Celsius, and how I measure it? I simply measure it by thermal contact, and then they're in thermal equilibrium, and then I measure 100 degrees Celsius. And here, I measure with a thermometer, same thermometer, and then I just measure it 100 degrees Celsius. And then you naturally believe this coffee of yours, this coffee of your friends are in the same temperature. Is that right? 이해 가시죠? 그러니까 이거 근데 여러분들, okay, so I mean, how do you believe it? By the way, how do you believe that? I mean, you're saying it's thermometer, but how do you believe from the beginning that's thermometer? They can do that kind of job. That's based on George's law of thermodynamics. Is that right? If you don't believe the George's law of thermodynamics, there's nothing you can do anymore. 이거 무슨 얘기인지 아시겠죠? 네, 그러니까 이게 사실은 되게 트리비얼해 보이지만 사람들이 이거를 믿기까지도 꽤 쉬운 일이 아니었다는 얘기예요. Okay, so George's law precedes in the first and second law of thermodynamics. You need to believe it before you do anything further. So let's talk about the function named temperature, how that coming along with the George's law of thermodynamics. So again, that there's no such function like temperature, but people believe this wording over here. They just believe this word. But in this wording, in this sentence, they don't talk about the temperature. They're just only talk about the thermal equilibrium only. They don't know what will become, just what kind of things will happen in thermal equilibrium. They don't know, but they just know thermal contact, and then that'll make a thermal equilibrium. That's the only thing they know. Okay, so out of that sentence or George's law, let's do some, it looks weird. proof. I mean, it's not really proof, some derivation. Just bear with me. I mean, there are something kind of moving, left-hand side and right-hand side, but, just try to follow the logic only. You don't need to remember any of these derivation here, but, this is actually the one of kind of thinking, logical thinking problems. So I think this is a good practice for you. So let's do this. And then direct law is obvious. And then I've already, repeated it twice. So I'm not going to just read it again. So again, as you can see in this figure down here, so you have the systems A and then B in thermal contact, and then they are in thermal equilibrium finally. And then system B and C are in thermal contact, and then they are now become the thermal equilibrium at the end. And then this C and this C, definitely the same C. That's what you need to know. And then there's a term diathermal wall. Do you know what that is? Diathermal. 혹시 이거 아세요? diathermal이 뭔지? 잘 모르시는 거예요? Okay, it's not really the opposite, but it's like opposite of adiabatic. Okay, adiabatic, you know that, right? No heat transfer. Okay, so the diathermal means, you're allowing heat transfer. So thermal contact, pretty much. Okay, so that's what it is. Okay, and then for C, so let's just kind of read one by one all these points. I'm gonna just kind of do that. I'm not gonna skipping any of these lines, and then I'll ask you a question, but you can just stop me if you have any question in the meantime. Okay, so by the equation of state for system C, its equilibrium state can be determined by measuring, we don't know the temperature yet, okay? So by measuring pressure and volume, or other two independent properties. That makes sense, right? So I told you earlier, if you know two independent properties, you can set the thermodynamic state. Again, we're going to come back to the point. But anyway, for now, two independent properties will set thermodynamic state, or your system C will be uniquely specified. Okay? So does this make sense? 이해가세요? Yeah. Okay. Okay. So then the next, from observation, this is an important point. So from observation, you're doing experiment. And when thermal equilibrium between systems A and C, in the left figure on the previous slide, so A and C are diathermal wall, and then they are in thermal equilibrium. And then people observe that when the thermal equilibrium achieved, I can give you only single property to determine the equilibrium state of system A. Okay, so in this case, I'm assuming I know thermodynamic state of C, and then it's in thermal equilibrium with system A. So typically, in general, how many properties you need to know to determine the thermodynamic state of A? How many properties to determine the thermodynamic state of A? Very good, you need to know two. But what people observed, if this A in thermal equilibrium with C, and then C is given by PC and then VC, for example, we know that. And then to determine this A's thermodynamic state, I only need to give one property. I don't need to give two properties. That makes sense, right? So meaning, what I find out through multiple of experiments, I just kind of do that experiment the same, many times. And then once I give PA, I know I am given VA, or if I'm measuring VA, I'm given PA. So that is just one or the other. They are dependent on each other. So I just give you one, and then that determines the thermodynamic state. So meaning, I just need to know one, which is reduced by one. when in this thermal contact with the system C, or thermal equilibrium with system C. So, as a functional form, that looks like this. So meaning, again, I know PCN and VC, that's known. That's what I'm assuming. And then once I know PA, I know VA, that's what I observed. If I know VA, I just, know PA. Okay? So this functional relationship makes sense to you, right? 이거 이해가시죠? 괜찮아요? Okay, 좋습니다. Okay, so then I can rearrange this equation for PC, and then PC now could be a function of these other three variables. That's doable. Okay, I just gonna move one kind of to the other side and make it explicit for that kind of function for that variable. Sorry about that. And then we can do similarly for the system B and C, which was on the right figure in the previous slide, and then we can have the same functional form, but instead of all A's here, now we have all B's, but because it's in equilibrium with C, we still have the same VC, VC, and then PC, and then PC. So, because this F1 and F2 are totally arbitrary function we can select, and then this but still gives the value of PCs, and then we can equate these two equations, and then we just remove the PC, which will give us this F1 is equal to F2. Okay, and then we can again rearrange this F1 is equal to F2 function for PA, which will give us other arbitrary function of G, which has a functionality of, so if we just, take out the PA only, you're left with VA, VC, VB, but VC, this is the same. So you have, so you have the PB here. So you have these four variables function of certain arbitrary function G. 괜찮죠? 여기까지. So 그냥 이거 뭐 하는 짓인지 별로 궁금 안 하셔도 돼요. 그냥 따라오시면 돼요. 일단 뭐 했는지만 그냥 쭉 보시고. 네, 그럼 넘어갈게요. Okay. Okay. And then that's up to the point where we have the AC in equilibrium, BC in equilibrium, and then in some way we just combine the functions from those two different experiments. And then this one in the next slide is now we are believing. This is to start with believing the Zerf's law of thermodynamics. And then this Zerf's law, what it tells us is, okay, so A and C in equilibrium, B and C equilibrium, then I know. I don't need to do the experiment. I know A and B in thermal equilibrium. That's the Zerf's law. And then if you believe it, and then systems B, A, and B are in thermal equilibrium naturally. Is that right? Does it make sense? 이거 이해가세요? 헷갈리시면 말씀하셔도 됩니다. 예. 예, 가시는 거죠. Okay. Okay, so systems A and B are in a thermal equilibrium, and then we can do the similar thing like we've done for the A and C or B and C. We can do the same thing for the A and B, and then we are coming up with this in a certain arbitrary function. So if you measure, or if you can set the thermodynamic state of B, for example, PB by PB and VB, and then only one parameters are needed, or properties needed to determine the thermodynamic state A. So that's what this function is, similarly. And then we can just rearrange it for PA, the same thing. And then now PA is a function of this. And then in the previous slide, the last equation we derived was this guy. Yeah, it was complicated, but this was the last equation we've done in the previous slide. And then we just got this PA, new PA out of this. Okay, so this is from previous slide. Okay, so meaning these are the same PAs, and then these are some two arbitrary function g and f3. But if you just take a look at the arguments of function g, arguments of f3, so we can just cross out the same guy. So we have the VA, we have the PV, and then we have the VB. But in function g, it was required to know the certain thermodynamic property of C, but from the theory of thermodynamics, because we magically know system A and B in thermal equilibrium without touching it and then making them thermal equilibrium. So that's why we don't have any functionality with respect to the system C in function f3, but in function g, because we start with the AC and then BC, we just left with that BC. But these two PAs should be the same. So meaning, out of this function g, this VC wasn't needed to determine PA. I mean, in function g is needed, but the VC is not really needed. And then this g function actually came out of f1 is equal to f2, if you remember in the previous slide. So let me just come back. So I'm just kind of talking too far. So this g was from f1 is equal to f2. Okay, so g was from f1 is equal to f2. So this g was from f1 is equal to f2, the same guy. And then out of this formulation, what should be true is, in general, there shouldn't be the function, just to determine the PA, and there shouldn't be any need for the, VC information. But still, F1 is a function of VC, including VC. So meaning F1 is still function of VCs. F2 is still function of VCs. But what it tells you is this VC's function should be canceled out with each other when you equating this F1 and F2. Only in that way, this final function G is not anymore function of VC. Does it make sense? 말이 겁나 길었는데요. 한국말로 할까요? 예, 뭐 잘 이해하실 것 같아요. 그러니까 이 G라는 펑션이 F1이라는 펑션하고 F2라는 펑션에서 나왔었고요. 근데 F1하고 F2는 separately VC가 필요한 펑션들은 맞아요. 걔네들은 맞는데 그 맞는 펑션 건 맞는데 결국 G라는 걸 거기서 유도를 했고요. 근데 따져보니까 우리가 만약에 영법칙을 믿는다 그러면은 실제로 PA를 아는 데 있어서 VC가 필요 없다라는 거를 요 관계식에서 얻어낸 거죠. 이쪽 관계식에서. 그러다 보니까 이 G라는 펑션이 여기서 유도하다 보니까 VC라는 게 마치 필요한 것처럼 보였지만 실질적으로 PA를 결정한 데는 필요가 없었다는 얘기죠. 그러다 보니까 결국 이 펑션들에서 F1과 F2라는 펑션들에서 걔네들은 VC라는 애를 아규먼트로 갖고 있는 펑션이에요. 근데 그 VC의 펑션이 양쪽에서 캔슬이 돼야 된다는 얘기지. 이퀄러티 상에서. 혹시 여기 이해 가세요? 예, 좋습니다. Okay, so this is actually how you make the function, to that VC function canceled out, and then this is forms. So if you just take this form, you can see that this coefficient added, they will be just canceled out with each other, and also once you cancel that out, now you just left with these terms in front, this first terms, this one and then this one. Because this one has the same multiplication of the function of VC, they also will be divided out. So you finally left with certain arbitrary function phi, which is only a function of Pn and VA, or function B, which is a function of PV and VB. Okay, so that's what's required in general. So once you've done that, in this equation, and then having this form, and then finally what you're left with is simply this. So what that means is, if you have thermal equilibrium between certain arbitrary object A and B, they're in thermal equilibrium, there is certain arbitrary function phi which should be the same in those two objects. Does it make sense? So that function wasn't known yet, but there should be certain function which is a function of its own thermodynamic state. So PA and VA is given, meaning the thermodynamic state of A is given. So phi A is certain thermodynamic property out of the given thermodynamic state. The same thing true for the phi B. But what it says is if A and B, arbitrary object A and B in arbitrary situation, they're in thermal equilibrium, and then certain function called phi in A and a phi in B should be in this, should have the same values, same numbers. Okay? And then you can actually extend this logic to A and C, B and C, but you can extend that logic to D and C, E and C, F and C, or any arbitrary object N, C, and then you can do the same thing. And then what you come up with in the end is this guy over here. So if we have thermal equilibrium between A and B, or B and C, or C and D, or A and D, A and E, A and Z, or whatever, if we have thermal equilibrium, there should be certain function called phi, and then have the same values throughout. And then people say, let's call that as temperature. So meaning the temperature is the thermodynamic property which will have the same value if we have thermal equilibrium. 이거 어떻게 이해 가십니까? 이해 안 갔나요? 이해 가셨나요? 네, 계속. 네. Okay, so this is actually the end of drift flow and then a temperature discussion. So, all right, so questions? If no, I'm gonna move on. 괜찮으면 넘어가겠습니다. Yeah, okay. All right, the second lecture note. Okay, so second lecture note is about the equation of state. 네, 상태 방정식이죠. Again, the equation of state. Okay, equation of state is the functional relationship among the state variables or thermodynamic properties for a important thing, equilibrium system. Okay, so that's the historical. And then the EOS is about equilibrium system or state. And then again, historically, it's typically given in PVT relationship because they are easily measurables. So there are many kinds. There is the ideal gas equation of state. If your substance or if your gas can be assumed as an ideal gas, again, there is no such thing like ideal gas in real life. Ideal gas is assumed state. So every real gas can be assumed as an ideal gas if it behaves like an ideal gas. Okay? Does it make sense? 이상기체라는 건 세상에 있는 게 아니죠. 그냥 여러분들 모든 substance가 이상기체가 될 수 있어요. 물론 이상기체의 조건을 만족시켜야 되겠죠. Okay, and one of the big condition in symbols for the ideal gas is this guy over here. So density becomes 0. Or what about this way? Specific volume. How the specific volume becomes to be assumed as an ideal gas. What should that specific volume becomes? Okay, very good. And because the specific volume is reciprocal to density, so that should become infinite. So what that means is specific volume is the volume divided by the mass you have. So meaning in a given amount of substance, given amount of molecules, your volume is large enough and then your mass is so tiny. What that means is your molecules, particles, are very much separated, and then it's all kind of vacancies in your volume, and then that's your ideal gas state. Ideal gas-like state, I should say. And then once your substance behaves like an ideal gas, your macroscopic properties then will follow this functional relationship. PV is equal to nRT, that's what you know. Or you just divide by number of mole for this volume, and then you can just use that, and then that'll give you this specific volume. So whenever you see, okay, let me tell you, this is the specific volume as given by extensive volume divided mass, or whenever you see the bar on top of the small letter, and what I mean by that is extensive volume divided by number of moles, okay? So this is still specific, so divide by a certain quantity of your substance, but now it's divided by mole. And it's still called specific volume, but per mole basis, okay? So this is the PV over T you're seeing over is equal to 1. And then for real gases, so what that means is if your real gas not behaves like an ideal gas, so your real gas now just being a real gas, and in that case you have other options, other equation of state. You can still describe the functional relationship between PVT. And then one good example we're going to talk about today is van der Waals equation of state, which is a form of this, and then we're going to go into that form detail. And then, or you can use the compressibility factor, you can use the video equation of state, dot, dot, dot. You have many other choices out there. So, I mean, actually, this is a one important thing I need to kind of make here. In thermodynamics problems, writing out the first law, writing out the second law is not a problem at all. I mean, those are all arithmetic calculation, plus and minus. I mean, just, just final energy minus initial energy is equal to in minus out. That's all simple calculation. What's difficult about the thermodynamic problem is how to know the thermodynamic properties, how to find out the energy, for example, energy for your substance in your system or experiment, or how to specify the thermodynamic state or by what kind of properties. Those are hard one. So finding out the right property, that's always hard. And once you have all the information, all the thermodynamic states and properties and energies and everything, and then write down the first and the second law, that's just piece of cake. I mean, there's nothing wrong with that. I mean, that's pretty easy. So there are tons of, equation of state you can find out for your specific substance in your experiments. So if you're doing experiments with the air, there are tons of equation of state for air. If you're doing experiments with the CO2, and then you can find out tons of equation of state for your CO2. So, but you will find out that at some point you not have that well-defined thermodynamic properties or equation of state, and then in that case you need to assume something, like you're assuming, okay, so my substance will behave like an ideal gas. I know there could be an error, but that's all I can do. So so forth and so forth. So this equation of state is that important, and then just keep that in mind. It's not just ideal gas equation of state. There are so many equation of state you can find out, you can use for your own research and then thermodynamic analysis. Okay, so this is the kind of some general comments about the equation of state. Any questions up to this point? 혹시 질문 있어요? 네, 알겠습니다. 감사합니다. Okay, so to begin with, let's talk about the equation of state of an ideal gas. And then, is that really something bad I never use anymore because I'm in the graduate school, and then I'm not going to use the ideal gas assumptions anymore because that's too simple? Okay, so let's just judge that and how good or how bad it is. Okay, so again, the ideal gas, what I mean by ideal gas, again, there's no such thing ideal gas in real life. And then that just happens for your real gas at very low densities, and or in the limit, density goes to zero. And then in that low density, average distance between molecules, so particles are well separated enough, and then they don't fill with each other. So there's no intermolecular potential energy affect each other. Okay? So meaning particles are so much separated. I mean, if they're close enough, there's always pulling force. The attractive force we call that. And there's always kind of attractive force in between two bodies, two masses. You know what that is. That's just universe thing. You know that. And then if they are far enough, that force is weak enough, and then we can neglect that force in between, or intermolecular potential energy, we call that. Okay, so that's the ideal gas state. But that doesn't mean that they are finally heating each other. They can collide with each other because these particles are not stationary. If it's solid and they're stationary in that fixed position, but they're still vibrating. But anyway, gas or liquid, they're really kind of moving freely. And then at some point, if in an ideal gas like situation, they're still colliding with each other, but the collision, it just kind of once, for a long time. And then when they get close enough, now they feel that intermolecular potential really, and then hit it and then coming back. And then now they're just getting far with each other. So meaning that moment, the heating collision moment is short enough in the lifetime of these guys kind of moving, and then we can neglect that kind of short period of intermolecular potential. We still can assume the ideal gas behavior. So anyway, I mean, just too much information. Anyway, so that's the ideal gas-like state. You got that point, right? 이해가시죠? ideal gas가 어떤 상태인지. 네. And the equation of state for that ideal gas is given by PV over RT is equal to 1, or PV and RT, and as you like. And then this one, the use of this ideal gas equation of state in typical engineering application is okay. Okay, let's judge that. Okay, so if you do your experiment with gas, okay, let's assume that. And then, let's assume you're using the air as your experimental gas. And then what this plot here shows you is PV over RT. That's the same guy over here, but is equal to Z. Do you know what that is, this Z? Actually, I didn't mention in the previous slide. Do you know what that is? I know it's kind of long way to typing it. Okay. Compressibility factor. Okay, very good. Okay, you did the typing. Okay, so compressibility factor, or 압축성인자라고 하죠. 압축성인자. Okay. If in certain PVT condition, it results in G is equal to 1, then can I assume your gas behaves like an ideal gas? Is that right? Yes, it is. But, so this is the first condition. But in your second condition, you find it out Z is actually greater than 1. Okay. And then now you're departing from the ideal gas-like state, or Z is smaller than 1. That also you're departing from the ideal gas-like state. So Z tells you whether you're near the ideal gas-like state, or it's kind of has some departure from it, or it just now behaves like a real gas. Okay, so once you believe that, and then this is a G chart on the left-hand side. I know this is kind of too small of the axis numbers, but I'm gonna read it for you. Okay, this over here is your 1. Z becomes 1. And then here you have 0.9. This is 1.1. So meaning this is a 10% off, right? 10% plus minus 10% off. Okay, so if you see the other axis, and then this x-axis, this is the pressure in bars. And then if you take a look at the number, this is already 50 bar, or 50 times of an atmospheric pressure pretty much. And then this is 100 times of the pressure. And then different color, if you just take a look at, and then different color tells you different temperatures. And then you see that, just make it more thinner lines. And then this is your 300 Kelvin. And then this is the 500 Kelvin there. And then this is the 1000 Kelvin. So it's above the ambient temperature. So in typical engineering application, when you deal with the gas, you don't have much time going over 100 bar. And then you don't have much time go below 0 degrees Celsius in your typical thermal experiments. So meaning, more or less, you're working on in this region with air. That's typical. So if you take a look at that box, red box, what is the maximum percentage of error in Z in this box? How much error you want to have in Z, or just out of 1? What is the maximum value in this box of Z departing from 1? Very good. Yeah, that's somewhere over there, right? That's only 5%. So meaning Z, even at 100 bar, and then that's still 1.05. So meaning, if you assume the ideal gas for your air in that application, in that experiment, if you use the PV-nRT, ideal gas equation of state, how much error you have? 5% error in calculating either volume, pressure, or temperature. That's close enough, more or less. You have much of other errors in other measurements and in other things. I mean, I'm not saying that's negligible. Depending on your experiments, you better be, more accurate than that. In that case, you can actually look up the compressibility factor chart or other equation of state, not ideal gas equation of state. You can use it if you're concerned about that much errors. But most of the range under that pressure level, ideal gas equation of state for air in the ambient temperature and up, that still gives reasonable approximation. You got the point, right? 이거 이해가셨죠? Yeah. Okay, so to be more specific, I just kind of put the figure on the right, which is about the water. This is the waters, the real water, not the ideal gas. This is a real water. And then TV diagram, temperature versus volume diagram. You may forget already, but anyway, so for now, just kind of bear with me. So this is TV diagram, and then this is the vapor dome, if you remember. Okay, this is the vapor dome, and then, under the vapor dome, during the phase change, the pressure, if the pressure remains the same, temperature remains the same, so your isobaric line goes in parallel here. So those are the, typical characteristics. So these are all the isobaric lines, but doesn't matter. So what is this state? Okay, just for for the review. What is this state called? 뭐라고 하죠? 베이프 덤의 이쪽 볼륨 큰 쪽. 전혀 기억이 안 나시던가요? 뭐 saturated 뭐였는데? 혹은 뭐 포화 뭐였는데요? Very good. That's saturated vapor. And then what is this side? What is this guy? Very good. You remember it. Okay then. What you have on this side? I'm gonna just delete it again. What you have on this side? This hatched region. What is the state? Overheated. Okay, close. Okay, very close. Superheated. Very good. Okay, yeah, that's superheated. 기억하시네요? That's superheated vapor. So that's vapor. Okay, so I'm going to just delete it off. Okay, that's the saturated, superheated vapor. So it's like the vapor. And then you see these kind of dotted line and then the blue region on the right. In this region, if you use the ideal gas equation of state for your real water to calculate the volume, pressure, or temperature based on other two parameters, this will give only the errors less than 1% here. This is 1% and down. You get it? So this is the real water. If you go to high enough specific, this is a specific volume, high enough specific volume, or low density, yes, that's ideal gas region. And if you go high enough specific volume, then you can use the ideal gas equation of state, and then it'll give you less than 1% error there. But if you get close to the vapor dome, meaning you're get close to the liquid side, then now you have accumulated error, meaning gas now is condensed, and then they now have the intermolecular potential affecting each other. And then now they don't follow anymore the ideal gas equation of state. And in that case, you need to have real equation of state, or this like chart or steam table you've used so far. Okay. So again, the important thing point out here, ideal gas equation of state is very good assumptions for the real gases in ambient state. I mean, if you have the gases in the ambient condition, and then ideal gas equation of state is a very good approximation. And even for like this water or real substance, certain point in the this equilibrium space, you can always assume ideal gas for the real gas without any problem. Okay, so that's the equation of state for ideal gas, and then we have slight time left. Any questions about this? 괜찮아요? 예, 알겠습니다. 예, 예, 감사합니다. Okay, I think this will be the last slide, and then we're gonna just finish it up. Okay, so this is about the van der Waals equation of state for a real gas. Again, this was a kind of next try of scientists. Okay, so they don't like the ideal gas equation of state because they are being incomplete or inaccurate, getting to the kind of saturation point, and it's not going to work at all in liquid state. So they come up with this van der Waals equation of state, which kinds of working in the gaseous phase, like in the ideal gas state, and then close to the dome, vapor dome, saturated state, and also in the liquid state. So it can cover liquid and then vapor phase in that single equation of state. But as you can see, the formula looks like this. And then definitely this cannot accurately follow that real thermodynamic state. it could be only approximate. And some gases have better fit with this van der Waals, but some gases totally wrong. I mean, do not say totally wrong, but it's much better than the ideal gas equation of state, but still there's an off because this cannot, this simple form cannot describe that complex behavior of real substances, but still it's very much improved from the ideal gas equation state. Okay, so what scientists include in this van der Waals equation of state is the size of a molecule. Because if you remember the ideal gas equation of state, you have large volume, but tiny number of the molecules, meaning the size of the molecules in this entire volume, it doesn't count. I mean, it's negligible. So in ideal gas equation of state, we don't talk about the size of the molecule. Even if you have the CO2 as compared to the hydrogen, and CO2 is much bigger than hydrogen, but we didn't say whether this one should have certain parameter to reflect on that, size of the molecule. But in van der Waals equation of state, they include the effect of the size of a molecule and also this one missed in the ideal gas equation state, which is the intermolecular potential between the molecules. So those are two things. But in this case, intermolecular potential, if you remember, and then there are actually two parts. If the particles are separated enough, they have attractive force, firstly. So they're getting close together. And then, but once they get into a certain distance and a minimum distance, and then if they try to go beyond that closeness, then there is repulsive force. So there are two parts in intermolecular potential. So again, attractive and a certain minimum distance, and then now they're just pushing each other. So they never, just, bonded together. Okay. But in this van der Waals equation of state, we don't talk about that repulsive part. It's talking about cohesive, meaning attractive force only. So it's just kind of now, ideal gas, they are like that. So they are separated out. But in van der Waals situation, now they are considering this much. And then now they feel the attractive force. Those are the two things considering the van der Waals equation of state. Okay? 제가 오늘은 시계를 준비한 탓으로 제가 지금 이제 끝내야 되는 시간인 거를 알게 됐네요. 여기까지 해야 될 것 같은데 혹시 질문 있으실까요? 그리고 뭐 어차피 이거 끝나자마자 오피스 아워 있으니까 혹시 또 궁금하신 분들은 뭐 줌으로 접속을 하셔도 되겠고요. 혹시 질문 있어요? 뭐 질문 없다는 얘기죠. 알겠습니다. 그럼 여기까지 하고 뭐 다음 시간에 보는 걸로 합시다. 수고하셨습니다.